I love the unibody design Apple uses in their laptops. They're made from aluminum, or titanium, that's processed to give a polished and refined look with a tough surface. They use a similar process on their iPods as well. The colorful aluminum cases look painted, but the surface is actually a layer of aluminum oxide growing into the aluminum with a dye locked into it. What's really bizarre is that these layers come from carefully controlled corrosion, in other words, rust. Every piece of aluminum develops an airtight oxide coating on its surface almost immediately when exposed to air. Now, while we think of corrosion as a force of destruction, when used creatively by engineers, it can yield incredible utility as seen in Apple's products. To create the coating used on these products, engineers enhance the growth of that oxide layer electrochemically. Let me show you with a piece of titanium. I've placed a strip of titanium in this solution hooked to a power supply. Don't do this at home. This can be lethal. Watch what happens as I apply a voltage. We see bubbles coming off the electrodes. As I increase the voltage, the color of the titanium changes. We call this process anodizing. Here's what's happening. I'm growing a layer of titanium dioxide. There's a very thin layer there naturally, but as I increase its thickness, you can see the color changes as well. If we look at the strip I created from the side and exaggerate the scale, we can see that each color corresponds to an oxide layer of a different depth. The color comes from the interference of light rays that bounce off the titanium surface at the bottom of the transparent oxide and those that reflect from its surface. The thickness of the layer determines how those two rays interfere. For each thickness of the oxide layer, two waves of a specific color will be exactly a half wavelength out of phase, and so when they recombine at the surface, they cancel each other. The color observed then, if the light source is white, will be the complement of that color. Well, titanium is fascinating. Anodizing is of most importance for aluminum because the coating can be made thicker, more robust, and protective. To get vivid colors, we dye the aluminum and seal the surface to lock in the color. Anodizing aluminum starts out much like titanium. Using aluminum as the positive electrode, engineers first pass enough current to grow a thin barrier layer, similar to that which forms naturally. Then, as the anodizing proceeds, the current pushes this barrier deeper down into the aluminum, converting the aluminum above into a very porous oxide layer. It isn't a layer being put on top, but instead the reaction consumes and converts the aluminum. This is one of the reasons it's so effective at preventing corrosion. The pores in this layer give the aluminum a unique characteristic important for a consumer device: the ability to be colored. The pores formed on the surface have a honeycomb pattern. Inside these layers, one can place dye of any color. Once the pores are filled, engineers seal the layer by boiling the aluminum in hot water. This closes the pores, locking the color in forever. You cannot scrape it off without removing the aluminum. The toughness comes from the oxide being structurally similar to tough gemstones. Sapphire is an aluminum oxide with trace amounts of iron and titanium to give it a blue color. It's also the basis of ruby, the same crystal structure with chromium that absorbs yellow-green. Both materials are very hard, 9 on the Mohs scale. In a typical iPod, they use only soft anodizing, so that layer isn't quite as hard, but still more durable than paint. I just love anodizing, the natural occurrence of corrosion made useful for everyday objects. I'm Bill Hammack, the Engineer Guy. This video is based on a chapter in the book, 8 Amazing Engineering Stories. The chapter features more information about this subject. Learn more about the book at the address below.